Yes, so floating point addition. So this is the hardware related to. So this hardware is actually a combination of many modules, and this is just to this is also going to show you that the floating point addition process is a little different than a normal addition, because in a normal addition we are just talking about this adder over here. This adder over here, this is the only thing we have in a normal addition as we saw earlier. But you can see there are many things involved in a floating point adder. Okay, so what are these things? So let's start. When you're talking about a floating point adder, you have to unpack these numbers. Now, when you're talking about unpacking these numbers, what we do is we isolate the sign, the exponent value, and the significant value. That's the first thing that you're going to do. So see, these values have different bits, so there is nothing difficult in this unpacking process. So what you are going to do is just you're going to separate the first bit, the next 8 bits, and the next 23 bits. If you're talking about a single precision number, so for both these operands x and y, we are going to do the same thing. So we are going to separate the sign parts, exponent parts, and significant part. The second thing is to reinstate the hidden one. So for significance, the one was not stored with those numbers. So we are going to bring that one back, and then because in addition that one has its value, so we are going to do that as well. Convert operands to internal format. Identify special operands exceptions. So when you're talking about operands here, so we are going to identify if there are any special operands. For example, if they are d-normal numbers, or if they are zero or infinity. So if, for example, if you want to add something with infinity, the result has to be infinity. So these are as we have mentioned, that infinity and zero are similar to any other normal number, but we have just given them a different representation. So um, and if these numbers come, then you are going to treat them differently. So once you have these exponent values with you, what happens, the sign values, both these signs goes to another logic, which is going to determine what should be the final sign, right? Depending on what operation is required. For example, you want to add these two numbers and their signs are equal, then actually you have to add them. If you want to add these numbers and their signs are not equal, then you are basically subtracting these numbers. And if you want to subtract these numbers and their signs are equal, then you have to subtract them. And if you have to subtract these numbers and their signs are unequal, it is as if you are going to add them. So all of that is decided in this control logic, and which is going to decide the final sign. Now the final sign also is going to be determined during the process, because we don't know up till this point which of these two numbers is a bigger number, because the sign has to be taken of the bigger number if they both have different signs. Right. So what we are doing is, for the exponent values, we are going to just subtract these two exponents, and the amount of difference they have is going to be used for the alignment shift. As you mentioned, the exponent values have to be subtracted, and the same amount has to be shifted for the smaller number. Okay, to make these things simpler, what we have is a selective complement and possible swap. So selective complement and possible swap means that when you design this circuit, you have the complement of any one of them, X or Y. You don't make both of them possible to be inverted. And there is an option to swap these numbers as well. So you can have the value over here or here. That is also possible. So that is a different thing over here. So you can complement these numbers, selective complement. So you can complement any one of them, and you can also swap them if required, so that you give this right values to the adder. And you have to align the significant depending on which one is. So for example, so just going to show you over here. um, yeah, to make things simple, so what we do is, if we have got two numbers x and y, they both and so we don't know which one is smaller. So for the smaller number, what we have to do, we have to um, reduce its magnitude. We have to shift it. So either you can use a shift over here, or a shifter over here. This is one way to do it. So you have two shifters which can shift either x or y. But this is a little you can say expensive process because you need two shifts operation. So what you can do is have a single shift operation, say with only with y, and if x is the smaller number, then there is an option to swap these numbers as well. Okay, so the y comes over here and x comes over here. So this is a possible swap option that is mentioned in the slide. So if so you are going to ensure that this y is always going to be the smaller number, which because you are using just a single shift. So if you're going to subtract x, add x with y, but y is a smaller number, that's okay. But if you want to add x and y and x is the smaller numbers, then what you can do is you can have a possible swap. So this means that this number goes over here and this number goes over here, right? Because the shifter is only given with y, right? So this is one thing. The other thing is also with the complement. So if you want to have a complement of this number to for example, you want to have subtraction operation and their signs are equal, which means that you are going to add the complement of a number. So you don't provide the complement with both of them, you provide the complement with any one of them, and then you can have that number converted into a different form. So for example, you want to do x minus y. If the complement is available with y, that's fine. If you want to do minus x plus y and the complement is only available with y, what you can do is convert this into another operation, which is minus of x minus y. So here you need two complements. So you have the final answer also complemented, and the complement is was with y. So you have complement. You're going to complement y, do the addition, and then the final answer is also going to be complemented. So these are different design issues that you can have over here. So that's all shown over here. So there was a comment here. What's the comment here? Okay. Right. So selective complement, possible swap, and then you are going to align the significant. You are going to add them. As you have mentioned that after adding these two numbers, they can be some normalization. If you're just if they have the same sign, then they can be a single normalization, single bit normalization. And if they have different sign, then because of subtraction operation, two different operands can have same magnitude, and if you want to subtract the same magnitude operation, then the result is very close to zero. So if you want to normalize that, it's going to have more shift operations involved. Normalization is a process where we say that there should be a single one before the decimal points, and in order to do that, we are going to shift the numbers and increase or decrease the exponent values. So after that, we can have a rounding operation as well. Now remember, there is another normalization after rounding. So if when you're going to add two numbers, sometime it might happen that you are going to normalize that number, and if you're going to normalize that number, then you're going to round that number, and if you're going to round it, it might happen that because of those rounding, you need another normalization, right?
Sir,
So you're going to
normalize
see
mean
that
round off?
of these two normalizers, only one of them would be used. So either it would be normalized over here or over here, so not both at both time. So sometimes the exponent values are same, and you get a value which is closer to which lies between 2 and 4. So you are going to round it out and then normalize it, right? Sometimes you are going to get some result which is very small, and then you're going to normalize it first, and then you don't really have to round it because the result is there. So okay, so this is the complete diagram of that, and then the exponents are added together. So this adder is going to give you the result. So the exponent value is going to be taken from from the bigger exponent, and this is the multiplexer which is going to tell you which is the bigger exponent, and you are going to select that exponent. If you need to add one or two one more to that number, because of normalization process, that is added to the exponent. And if because of subtraction process you need to subtract a lot, that is also required over here. So final exponent value has an adder as well. And then this is the final step where you're going to pack it out. So when you are going to pack it, you combine the sign, exponent, and significant values, remove that hidden one, and if there are any special outcomes, you are going to identify that. For example, you want to add two numbers having same signs, having different signs and the same magnitude, uh, with same exponent, are going to get a result of 0. So if there are some special outcomes of that operation, that has to be also mentioned over here. So you can see this is the whole hardware, and this is a combination of many modules. So this is your adder, which we have discussed. Then there are some shifts, and normalizing, it means also shifting operation. And then there is a the big thing is this control and sign logic, which is doing all these tasks, right? So it is identifying what operation is required by that adder. It should be addition or subtraction. It's also identifying how much value should be for the normalization part, and exponent values and final sign. So the main thing is this control and sign logic, which is a difficult thing. So in floating point in floating point numbers, addition and subtraction is a difficult task, right? So you can see from this design here, but this is the main step involved. So if you're given two floating point numbers and I ask you to add them, the first thing that you have to do is to unpack these numbers, take the exponent value out, find their differences, make them align if required, and add them, and then normalize them, and then you are going to join them back, which is called as packing, right? So this is the floating point addition hardware. If you talk about multiplication is a simple operation in floating point numbers. So if you have got two numbers, s1 and s2, this is a simple thing to do, because the significant values are multiplied and their exponents are added. Okay, so we have discussed multipliers, so you can use any multiplier you want over here, and then the significant values are multiplied, and their exponents are going to be added. Okay, now because you are doing a multiplication operation, the possible answer is going to lie in 1 to 4. Why? Because S1 can have a value from 1 to 2 and S2 can have a value of 1 to 2. Here we are not talking about aligning these two, so we are not talking about adjusting their magnitude. So both of them go with 1 and 2, 1 and 2. So if both of them have the magnitude 1, then 1 multiplied by 1 is going to be 1. And if both of them have a magnitude 2, then 2 multiplied 2 is going to be 4. So actually none of them are going to be 2. So this means 4 is not possible. So that's why we have shown that as a round bracket, right? So our final answer is going to be lie between 1 to 4. Again, the same thing, that this range has got an acceptable range and an unacceptable range. So the acceptable range is 1 to 2, and the unacceptable range is 2 to 4. So if your answer lie between the range 2 to 4, then you just need a single normalization shift. Okay, so that's called a post shifting, that is done after the result. So remember, in addition we were doing pre-shiftings, we were trying to do it before the process, and we were doing post shiftings as well, but here we don't have any pre-shiftings, we just have post shiftings. Okay, and exponents are just added together, and when exponents are added together, it might happen that you find out that this is not possible. So for example, you want to add two numbers together, one has an exponent of 120, another has an exponent of say 50. So 120 plus 50 would become 170, right? But the maximum that you can go is 127, because 128 is reserved for infinity, so you cannot have 150. So that's the case of overflow, right? So overflow can occur in multiplication, right? If you're talking about division, again, it's a simpler process than addition, because what you are going to do is you are going to divide the exponents s1 with s2, and you're going to subtract divide the significant and subtract the exponents, right? So this is again a small process here. Now if both of them can lie between the range of 1 to 4, their final answer can be from 0.5 to 2, right? How is this possible? 0.5 to 2, anyone?
So dividing
When we are going
dividing
to
one by
divide two
one.
numbers, what is the final range that we are going to get? It says 0.5 to 2, and both with round bracket. Can anyone justify this? Come on, that's simple. So how do we get point 0.5?
So by dividing 1 by 2, one number is
So the
1 and
least
the
number
other
that
one.
we can have is point 0.5, not 1. How do we get 1.5? Yes, anyone? Okay, I didn't see this chat. So Fahad Khan has written 1 by 2, right? Fine. So 2 is not possible, right? So this means that point 0.5 is also not possible. So that's why we have a round bracket with point 0.5, because the number would not be exactly 2. So it would be close to 2. So then we are going to get an answer close to point 0.5, right? Okay, so right, Fahad. So it would be 1 divided by 2. And how do we get 2? That's 2 divided by 1.
2 divided by
Okay, so
2.
if your first number is 2 and you're dividing it by 1, that's the smallest value that you have, that's the biggest value that you have, then the maximum value that you can get is 2. And if the smallest value is 1 and the biggest value is 2, then the value of division is point 0.5. So that's easy, right? So and subtraction result. So if you're going to subtract the exponent, then it might happen that you get an answer which is going very small, and then there can be again overflows or underflows in division normalization. So let's look at the hardware for that. So let's look at how to do division and what's the hardware required over here. So we are going to multiply two numbers. So we have discussed that we need post shifting. So this is the hardware for multiplier. Now this is a simple thing. Now you can see if you're going to compare this with the adder, with the floating point adder, you're going to see this is quite simple because first of all it does not have any control logic. So it's a simple thing and it's very easy. So again you're going to unpack the number and the two signs that you have, just simple XOR them. So if both of them are zero, you're going to get final answer. So if both are positive number, positive number. If both are negative number, a positive number. If one of them has a different signs, then it would always be a negative number, right? So a simple operation for that is an XOR. Add the exponent, that's the multiplication operation. Multiply the significants. Normalize them because we said that we can need only a single normalization and not just exponent. Round them if required. If the normalization is not required, you are going to round them, and after rounding you might require a normalization and adjustment. So any one of these normalizations is going to work. And finally pack that. So that's a simple thing, right? You can see that it's quite simpler than the adder. So we have talked about the multiplier. So if you're going to multiply significant, we have talked about different multiplication schemes in our earlier operation. And division is a simple process like this. So you can do the same for division. Division operation, instead of multiplier, there would be a divider. Instead of this adding, you are going to have a subtractor over here. Okay, so let's come to our final topics of floating point numbers. We have rounding schemes here, how to round the number in IEEE 754 format. So IEEE 754 defines 5 different rounding schemes, and the default is the second one, round to nearest ties to even. So the first one is round to nearest ties away from zero. So how are we going to do that? So when you're talking about round to nearest ties away from zero, this means that you round to the nearest integer value or the round to the nearest number value and tie away from zero. So go for the number which is bigger than zero, right? The second is round to nearest ties to even. So if you have got a tie, then go for the number which is even. The third is round towards zero. That is, if you have got to round, go for a number which is closer to zero. Round towards plus infinity is to go to a number which is closer to plus infinity. Round towards minus infinity is to go to a number which is closer to minus infinity. Okay, so I'll just so these are simple modes, and sometimes student gets a little confused in one and two, and what is the difference between these two. So I'll just give an example: round to nearest ties away from zero, and round to nearest ties to even. So if you have a number, I'm going to talk in terms of decimal digits because it makes things much simpler. So let's talk about the first one, round to nearest, ties away from zero. So if you have got a number like this, 7.57, and I ask you to round it to a single digit after decimal point, so what are you going to do? You are going to make it 7.6, right? And why have you done that? That's the first scheme, round to nearest. Nearest means that you want to have it as the nearest number. So 7.6. Your options are 7.5 and 7.6, right? For a single digit after decimal, your options are 7.5 and 7.6. Round to nearest means you are going to find out the nearest one. So what is the difference between these two and these two? So you have a difference of zero point 0.7, 0.07 over here and 0.03 over here. So you are going to go with the nearest number. So round to nearest. And then the other thing was tie away from zero. Now tie is a different thing. So I'm going to come back. Ties away from zero, ties away from zero, and the second is ties to even. That's the default. So now I'm going to come to what is tie over here. So tie means that your rounding is actually tied. Okay. So now I'm going to come to the to another scheme in the same thing. So let's go with 7.55. Now if you have got 7.55, so the options you have are 7.5 and 7.6, and both of them are now going to give you zero point 0.5. So that's a tie, right? So that's a tie. What to do in this case? So the first scheme says round away from zero. Away from zero means go for a bigger number. Away from zero means if you're talking about the positive side, go for a bigger number. And if you're going to talk about negative side, again go for a bigger negative number, right? So away from zero means you're going to select 7.6 again, because this is number which is away from zero, more than 7.5. Okay, are you getting this? Okay, so let's come to the second, which is
Last point
uh,
I didn't get it.
so I'm going to talk about tie in this case. Okay, so we are going to talk about the second option, which is round to nearest ties to even. So round to nearest and ties to even, that's the default. That's also explained over here as well. So when you're talking about round to nearest and ties to even, the main thing here is that if there is a tie, then you go for the nearest even number, right? Okay, so in this case, 7.55. So if if you talk about two numbers here like 7.5 and 7.6, so the even number is going to be considered as 7.6, right? So if there is a tie, go for the even number, 7.6. Let's take another example for the same scheme. Let's talk about 7.45. Now I need answers from your side. So what will 7.45 do in the first scheme and the second scheme? So here the two options are 7.4 and 7.5. Yes, answers. So we are talking about second schemes. So second scheme means round to nearest ties to even. So there is a tie. Both of them are zero point 0.05, difference of zero point 0.05. Either you go to this or this. So then you go for even. So which one is even? 7.4.
7.4.
So 7.55 rounds to 7.6, but 7.45 rounds to 7.4. Okay, so this is the default over here. Now why do we do this? This is done because sometimes these errors, if you keep on accumulating these errors, it happens that they grow up. The error grows up. It's always a positive error. But when you're talking about doing it in this way, it might happen you get a positive and a negative error, so the accumulation is reduced, right? So this is the default scheme. If you talk about in the first scheme 7.45, so 7.45 in the first scheme would go to 7.5, because that's around to nearest ties away from zero. So away from 0 is obviously 7.5, not 7.4 in this case. Okay, I hope you get this. So if there is a tie, then you go for the bigger number in the first scheme. If there's a tie, you go for the positive number in the second scheme, right? So this is the only difference here. And then we have the other schemes which are quite simple, like round towards zero. This is shown in the diagram as well. This is the second option, round to nearest dice to zero. That is, if you have a number which is lying between which is this dot over here is showing you where it is going to go. So the tie is going to happen at zero point 0.5. So zero point 0.5 means that it's going to be rounded to 0, and 1.5 would be rounded to 2, and 2.5 would be rounded to 2 as well. So this is nearest even number, right? So 2 and 4. So you're going to see whenever there is a tie, it goes to the even number. Okay, round towards 0 means towards 0 is an invert thing. So if you have a number like 3.45 and you want in all these 3, 4 and 5 schemes, you are going to see that it's kind of a truncation operation. It never says that you have to round to the nearest. It says round towards 0. So if you have got 3.2, that's going to go to 3, and if you have got 3.9, that's also going to go to 3, right? So round towards 0 means go towards 0. It never talks about rounding to the nearest first and then going to 0. Okay. Round towards plus infinity means go away from go towards plus infinity. So everything goes to plus infinity. The negative side also goes to this side, and the positive side also goes to this side, right? And round towards minus infinity means everything goes to minus infinity. So the positive side goes to the one which is close, which are closer to 0, and negative side go towards minus infinity. Okay, I hope this is clear. Right, so the last topic over here in this scheme is how many bits do we need actually to preserve our precision, preserve our number precision while addition. So the answer is we just need 3 bits. We just need 3 extra bits in the adder, and if we have these 3 bits, our result is preserved. Our final result is going to be the same as if you have got uh, many bits. So if you have got even the whole bits that you are required to store the shifted amount, these 3 bits are only going to be enough as well. So that's the conclusion here. So the guard bit, the round bit, and the sticky bit. So we call them as the guard bit, round bit, and sticky bit. So why actually we need 3 bits to give our result? This is because I have to explain this thing. Okay, so guard bit, round bit, and sticky bit. And now let me just tell you, we have got 3 different ranges here. So we have numbers like so when you are going to round them, there are going to be numbers which are less than 0.5, and they are going to be numbers greater than 0.5. I'm just giving you an example, zero point 0.5, because this is how we do it, right? So whenever we are going to talk about any level that you want to, so you can just have the half of that, and that's going to be called as zero point 0.5. So we have got numbers which are going to be less than zero point 0.5, and we are going to have numbers which are greater than zero point 0.5. Then there is another range which is equal to zero point 0.5. That's the one which we are talking about, the ties one, right? So actually we don't have 2 possibilities, we have got 3 possibilities. So 1, 2, and 3. So whenever you have got 3 possibilities, the number of bits that you are required to select any one of them are going to be 2. So 0, 0, 0, 1, 1, 0. You need at least 2 bits to represent these options, right? You cannot do that in a single bit. So there are 3 possibilities and 3 ranges when you're rounding. So when you have number less than 0.5, this means that um, you're not going to add something more to it. So that becomes 0. And if you have got number greater than zero point 0.5, you when you're rounding it to nearest, you get a 1 because you have to uh, increase the magnitude. Now when there is a tie, then there are different options, so it can be a 0, it can be a 1, right, depending on which rounding scheme that you have selected. But the main thing is just you just need 2 bits to decide that, right? So why 3 bits in this case? Now the tricky part is this zero point 0.5. Tricky part is this zero point 0.5. Okay. Now what happens when you are going to shift numbers to the left, to the right, sorry. So if you have got a number like 1.010111, and this number is a smaller, has a smaller exponent, and then you have to make the exponent same. And maybe for that procedure, what you're going to do is shift this number to the right many bits. So we have shifted to 5 bits. So while doing that, and we are just allowed, say for example, to keep 6 bits over here. So that's the only thing that we can have. So if this is the so this means that all of these bits have to be shifted out. Now when you're going to shift this thing out, then the final result might be different. So what you do is you just keep 3 bits. Now of that third bit, which is a sticky bit, it's actually called sticky bit because any bit which is shifted out, if it's a 1, then that sticky bit is going to be 1. That's called a sticky bit, so it sticks to a 1. So any bit shifted out, so these bits are shifted out. So if any bit is shifted out, then if there is a 1 in any one of them, then the sticky bit is going to go 1. Now this is going to ensure that if you have a number which is something like which is something like let me just show you what is zero point 0.5. So we were talking about this range over here, this middle range 0. 0.5. Now if you want to express this 0. 0.5 in binary, 0. 0.5 actually in binary is something like this: 0.10000. So there are all zeros. If you have a number less than 0. 0.5, that would be something like 0, and then there can be any combinations of ones over here, ones or zeros, anything. But this has to be 0, which means this is less than 0. 0.5. And if you have a number greater than 0. 0.5, this means this is 0. 0.1, and there is at least 1 over here. Now this option of finding at least 1 over here is going to be different with this second and third, right? Because in second there is no 1, and in third there is at least 1. So how do you know that there was at least 1? So that's the sticky bit. That's the toss of the sticky bit. So any bit that is shifted out and it's 1, sticky bit goes 1. So if the sticky bit is 1, this means that you are lying in the third range, not the second range. Now this is important over here. So sticky bit is there to identify whether you are in range number 2 or range number 3, either 0.5, exactly 0.5, or greater than 0.5. Okay, so we need a single bit for that, and that's a special bit. So any bits that have been shifted out are going to be called. So we say that we have a sticky bit over here. So actually we need 2 bits. So we call them as guard bit, round bit, and sticky bit. So this means that I'm going to shift these 3 bits out. I'm going to keep the 2 bits and shift these 3 bits out. But these 3 bits out means that my sticky bit is going to be 1 because there was 1. What I'm left with 101, and these are the only 3 bits that I need. Right? Remember that last one, the sticky bit, is actually OR of all the bits that have been shifted out. Right? So the main thing that I have to tell here is that whenever you are going to add or subtract or do any operation on floating point numbers, you just have to keep 3 bits extra. And we said we just needed 2 bits. I'm going to come to that as well. But remember, the sticky bit is the OR of all those bits, and then these 2 bits are there. Now what happens when you're going to add 2 numbers? we say that we might get a result which lie between this range 2 to 4, right? So 2 to 4 has to be normalized, and you are going to put that thing over here, and that's okay. But when you're going to subtract that, so sometimes you get a range which is going to lie between 0 less than zero point 0.5. So I'm going to come to that. So when you have a number which lies between 0 and zero point 0.1, which is less than 1, so you have to make an alignment shift to make it in this range of 1 and 2. And this means that this guard bit becomes part of your answer. So if you have the guard bit as part of your answer for some cases, then you need these two bits, round bit and sticky bit, to identify which are the three ranges you are in, right? So this third bit, guard bit, is actually sometimes made part of the answer. So what we said was we just needed two bits to identify these three range. So why three bits were there if two bits are enough? So two bits are enough, but sometimes it happens that this guard bit becomes part of your answer. And if this becomes part of your answer, then you need at least two bits to find out what should be the next value that should be added to this to make it to make the number have the precision value less than unit of least precision by 2. So you have the error less than unit of least precision by 2, right? So that's why we have got 3 bits. So if there is a normalization shift actually taking place, then r is equals to round down, discard the part of unit discarded part is less than unit least precision by 2, and if r is 1, then the round part is discarded part is greater than unit of least precision by 2. So this round weight is going to identify you. If it's 0, then this means that you are talking about less than zero point 0.5. If it is 1, you are talking about greater than zero point 0.5. But the only thing left now is if you are actually zero point 0.5. If you are actually zero point 0.5, that is done by the sticky bit. Okay, right? So this is how these three bits are combined together, and these are the only three bits that are needed for rounding operations. Okay. I've given that chapter to you as well if you want to read that yourself. What why three bits are so the book has explained that in much detail. So you if you want to read that, you can do that as well. I've tried to explain that there is a ground bit which is a guard bit, sorry, a guard bit which is sometime part of the answer, which becomes sometime part of the answer if your magnitude lies in this range of half, sorry, 0.5. So if that is the case, then you have to do many normalization shifts, and then in that case you just have to make a single normalization shift to make it in this range of 1 to 2, and for that this guard bit becomes part of your answer, and these two bits are going to determine then the range that your number lies, and so that you have to add a 1 or add a 0 to make the final answer, right? So this is how the precision is handled. You can do some exercises as well to find this thing out. So I leave this as an assignment for you, because let's just go on with our new topic. So we can add two numbers. I leave these two as an exercise. I'm going to give them as an assignment to you. So you have to add these two numbers and multiply these two numbers. So these are 32-bit floating point numbers, and this is the sign bit, the exponent bits, and the significant bits. So go with the same process and try to add these two numbers and get the results. And this is the multiplication. Again, I've not shown the extra zero. There are many zeros over here. All of them are zeros which are not shown, right? And try to multiply these. So you're going to see that multiplication operation, you don't have to multiply all these 23 bits with 23 bits. You just have to multiply two bits with, get the hidden one also, 1.01 and 1.11. So you just have to multiply three bits with three bits, and maybe that would be easy for you. Some students keep on multiplying 23 bits with 23 bits. That's never required, right? It's because you have got always a 1.01 and a 1.11. So no, this is how you also multiply on paper. You don't write all those extra zeros after the decimal point, right? So you try these two out yourself. So I'm going to finish the topic of floating point over here. So this is our last topic, invalidated laws of algebra. So we see here in floating point numbers, many of the arithmetic laws that we have studied are not working. They don't work in floating point arithmetic. So for example, associative law of addition, if you do a plus b plus c, it's this is not equal to doing a plus b plus c, and this is shown with an example. So for example, if we have got three numbers like a, b and c shown as over here, and if we do it in the first way where we are going to add b and c first and then add it with a, so if we do this, then you're going to see that b and c are going to give you a result of 0.1239 times power 5. And if you are going to with a negative sign, if you're going to add them, what you're going to get is 0.2 into 10 power 1, right? And if you're going to do a plus b first and then add c to it, you're going to get a much precise answer, which is going to be 0.24321 in 10 power 1. So what happened over here? The thing, the main reason why you're getting a different answer is when when you were adding b and c, they were numbers which were having very different exponent values, right? So we had 10 to the power 5 and 10 to the power 1. So you shifted c out because that was a smaller number, shifted it out. And when you shifted it out, you removed all these numbers 4, 3, 2, 1 because they were insignificant, and you have to you don't have space in your adder to hold these numbers. So you left them out, and then you did the subtraction operation to get 1.13 right? And this is where there comes a difference when you do a final addition, and then you get enough. And this is the thing that you have to consider when you're talking about floating point arithmetic, that even for the computers that we have, uh, and the bits that they can hold, so they hold much more bits than required, but still there is a possibility that you are going to get different answers whenever you're going to do different tasks. Even you can check this out from the calculators as well. The calculators also give different answers if you are going to do it in a different way, right? So you can do that on your calculators as well. Try to find out, obviously not this particular example, but you can have your own examples. So you can see the result is quite different for both of these cases. So this law does not work. And then there are the other laws like associative law of multiplication, the cancellation law. So that associative law of multiplication was the main thing that we discussed in our first example when we were talking about arithmetic, which was the example of why the Patriot missile could not intercept the Scud missile coming from Iraq. And that was because the same reason, that they were implying that 1 upon 10 multiplied by 10 is going to give them 1, right? So that's not the case over here. Okay, so cancellation law is also not there. Distributive law is also not there. Multiplication, cancellation, division, that's also not there, right? Okay, so I'm going to stop the topic of arithmetic over here. So because we have got 40 minutes, 40 some minutes here, so I'm going to continue. So arithmetic topic started with adders, multipliers, dividers. We looked at different schemes, and then finally floating point numbers. So all of that is part of our arithmetic operations and their hardware units. Right. So next topic is instruction level parallelism. But before I come to that, I need some discussion from the class regarding how much have they studied about pipelining. So how much is right? So there are 9 students here. Okay. So I know about Shirina. She has studied over here. What about the rest of you? Uh, how many of you have studied pipelining, instruction pipelining before? Because that is how I'm going to move then. And be accurate in your description. How much have you studied that, or you are just new to this concept? Because normally we study the concept of pipelining in an undergraduate level. At undergraduate level, we discuss about instruction pipelining, just basic. Okay. So just basic means you are familiar with the concept of pipelining, stages, and other concepts related to how things are going to move, how instructions are going to move between stages, right? What about the others? Akash Ali, Hail Saeed Ahder, are you familiar with the pipelining concept? Mohammed Imtiaz, uh, Altaf, say Altaf Alisha, Yasser. No, new to this topic. New. Okay, right. So if all of you are new, so then this is going to be a little difficult because. Okay, I'll give you some assignments to do because I am not going to discuss the basics right now. Okay, I'm not going to go into detail of the basic. I'm going to discuss the basic, but I'm not going to go into much detail. Okay, so let's start. So when you're talking about doing an operation one at a time, this is possible, but it gets a little time consuming. And if you want to improve the performance, what you do is you pipeline that process. Now, what is pipelining? Now, this term pipelining can be used for different processes. So the main thing that you need is a sequential process. Sequential process means that there are sequential steps there. Things are coming one after another, so it's not nothing like doing something in parallel. Rather, you are doing it one after another. So I normally give an example to my students. So we normally cover this in an undergraduate course. When I give them examples, I give an example to students regarding their feature on that they submit at the bank. So what happens is that you have different steps to do that. So you are going to fill that form, write your name. It's going to take some time. Then you are going to go to the counter, pay your fee, and paying the fee means that you're going to give the check, give the cash to the banker, and the banker is then going to count that money, and that's the right amount, he's going to stamp it. If you have given something more, he's going to give return that cash to you and then stamp it. And then further you go to another counter where uh, there are some further processing required, or maybe the second counter is going to stamp it, whatever. So this thing is a stepwise process. You go to the bank and you do something, and then there is a task for the banker, and then there are tasks for stamping it. So let's, if we allow that a single student can go to the bank only, then what will happen? And if for example the whole process takes 5 minutes to do, and we are allowing just a single student to come to the bank and do these steps, so what will happen is there would be a long queue outside the bank because many students are waiting and you are just servicing a single person. Now, how to speed this thing up? Now, for speeding this thing up, we break this process into different steps. So, for example, what we can say is filling the form is one step, right? And we have a counter for that. So, we have built a room. So, if there is a student who wants to pay fee, he should first go to that counter, and in that counter we are going to allow just a single student. So once that student has filled his form, which is going to take say 2 minutes, then we are going to allow that student to go to next counter where he or she is going to pay the fee to the banker. Now, during this time when the first student has filled the form, what is going to happen? Now, if the form is filled by the first student, that counter is now empty. So when that counter is empty, this means you can bring in one more student into the bank, because it's not going to disturb the process, because the first student has filled the form, and now he has moved out from that particular that particular room that you have built for filling the form. So the first student moves to the banker, the second student comes to that particular room where he or she is going to now fill the form. So now you can see there are two people in the bank, and then the first one goes for to the banker, pay his fees, and that was in equal amount, and then the banker says to go to the third person who is going to finally enter some value and stamp the form. So he can then go to the third person, and the second person can go to the banker, and still now you have that room available for a third student to come in. So you're going to see what's happening over here is there is a much overlap and then you, instead of having just one student doing this, you're now bringing in three students, and they are doing their tasks in parallel, right? Now there are many things that you have to consider in this example as well. One thing is, how long is each process taking? Now you know that filling the form is sometimes a little difficult, or sometimes you can say the longest process required, because counting the money is much easier process and stamping the form is much easier process. But filling the form, so if we break this thing into three different steps, then we can have filling the form, giving the cash, stamping the form, right? And a fee is paid. So at one time what we can have is, at the first time we can have a single student, then in the second time we can have two students, then we can have three students, and then from then onwards we are always going to have three students in the bank, right? Each at a different stage of this process, right? And so they're not interfering with them. And why are they not interfering with them? This is because we have identified some rules for that, right? Now what will happen, let's say that one of the student is a little faster in writing and filling the form, right? So we have reserved 2 minutes for that. On okay, so one of the student, the first one, fills the form, goes to the banker for his cash. Then the second student comes in, fills his form very quickly, let's say in less than a minute, and then quickly leaves their room and goes to the banker. So there are now two people with the banker. Then the banker is going to go confused. So he's going to get confused, and he is probably going to be irritated. Who has given me what much amount? So this is not going to work. So we have to identify some rules. The rule is that if you have a particular stage empty, then only you can go to that particular person. So if the first one is with the banker and the second student has filled the form earlier than that, he cannot go to the banker until the first one leaves the banker, right? So if you're going to ensure that every student or every task is going to shift to the next one at the right time, then only you can have multiple tasks running in. Okay. Now we can apply the same thing to instructions. When we talk about instructions, we say that instructions have to go through a whole instruction cycle. Now, what is there in the instruction cycle? We fetch an instruction, we decode the instruction to find out what is required, we get the operands, we do the execution, we finally restore the result. So these are different steps that are required, right? So if you're talking about doing the same thing from instructions, what you can do is build a circuit which has all these operations and control unit designed in such a way that it can do only for one task. Or what we can do is we can divide these different steps into different stages, and then we prevent one step to interfere the other one through some register. Okay, so now I'm going to talk about the second option. How are we going to do that? So if we divide them into different stages and prevent them by some registers that they don't interfere or give their results earlier in time, then what can happen? So let's try to see here. So I'm going to talk about processor like MIPS, or they can be other designs as well, but the RISC type processor is much easier to explain because they are simple processors and they have simple tasks. So what are the steps involved in an instruction cycle in such a processor is you fetch an instruction, you decode an instruction, and when you decode an instruction you also read the operands. And we have assumed here that we are not going to read any operand from memory, so we can just read the operands from register. So the second stage is about reading the operands from register here, right? And then once we have the operands with us, we are going to do the actual execution, right? And then finally we are going to store the result in the fifth stage. Now, what about this memory stage here? This would be required by some instruction, but mostly not required by other instructions. So this is there for load instruction, which is required only by load. So if you're talking about a load operation, what happens in load operation is you get some value from memory into a register. So what happens in load instruction, you are going to fetch an instruction, decode it, right, get the address and calculate the address in the execution stage, and then you are going to get that value from memory, and then you're going to store it and put it in the register. So that's the 5 stages that is required. Remember that each stage is going to take some time, and then there is some barrier in between these two stages so they don't interfere. So what I'm talking about here is that instead of having a lumped circuit doing all these tasks together, I'm going to break that into different stages, identify those parts which can be separated. And for those parts, they are going to be separated with some register in between them. Now, what is the importance of this register? This register acts as a barrier between different stages. Now, when you're talking about combinational circuits, uh, these circuits, whenever you're going to give some input to them, they are going to give some results to you, right? And if you're going to change the input, they are going to give a new result to you. Okay, if you're going to keep on changing the inputs, they're going to keep on changing the results. Now, what is going to happen? If you're going to give some input to that, it's going to give some result. Now, if this result is allowed to be propagated to the next stage, this means that this stage is also going to keep on changing its result. But this register is going to prevent that. The register is going to prevent that because these registers are designed in such a way that they are working on a particular clock, and they are only going to accept the input at that particular clock. So any input which is coming before that clock is not going to be taken by these registers, and so the new combinational circuit, the next combinational circuit, is only seeing the value which is stored in the register. So it's not getting the new contents, it's just getting the values which have already been stored. So this is going to prevent it from continuously changing the results. So all of these are combinational circuits, right? All of these are combinational circuits, and the property of combinational circuit is if whenever you're going to give some new input to it, it's going to start doing some more calculations and changing it. But if there is a register in between that, and you are controlling the contents of these registers to be changed at particular time, then you are going to prevent the previous combinational circuit to give its result earlier in time. So these register act as synchronization barriers. So you are basically synchronizing the results to go from one stage to another. Now this is important. This is important because if you want to ensure that there are multiple instructions going on in the pipeline, then an instruction result should not disturb any other instructions result. Now, in terms of cycles, or in terms of timing, how is this thing going to proceed? Now, here we have shown in terms of clock cycles. So 1 to 10 clock cycles are shown over here. And these are the stages. And these are the instructions which are numbered as I1 and I2 and I3 and so on. So in the first clock cycle, so this is what's happening over here. In the first clock cycle, this is the beginning. So in the first clock cycle, the first instruction comes into the fetch stage. And all the remaining stages are empty. Okay. When the first instruction is fetched in the second clock cycle, so what we do is we shift that instruction to the next stage, right? So when an instruction shifts, it brings all the things along with it. So anything related to that instruction also have to shift to the next stage. So as instruction goes with all its inputs, all its processed and unprocessed inputs. So in the next cycle, what will happen is instruction 1 moves to a decode stage, and a new instruction comes into the fetch stage. Now what will happen, that the second instruction is going to be fetched. Then in the third cycle, the first instruction is going to move to the execution stage. The second is going to move to the decode stage, and another new instruction is going to come into the first fetch stage, right? So in the fourth cycle, what will happen is similarly, A new instruction is going to come into the fifth stage, and all of these instructions are going to move one more stage to the of the pipeline. Then you're going to see in the fifth cycle, the first instruction has moved to the fifth cycle, the second to the memory stage, the third to the execution stage, the fourth to the decode stage, and another instruction, the fifth instruction, is now moved on to the fifth cycle, to the fifth stage. Now from here onwards, you're going to see that this pipeline is always full. So you're always going to bring in a new instruction in a new cycle, and always going to get an operation completed at the end of one cycle, right? So how is this going to improve the performance? So instruction latency is described as the time it takes to complete an instruction. So here we can see that every instruction is going through 5 stages. So if we say the instruction latency is the time from the start of the instruction to the end of the instruction, we say that instruction latency is still 5 cycles. Okay, because instruction 1 is taking 5 cycles to complete, instruction 2 is also taking 5 cycles to complete, started at this point, ended at this point. So any instruction that you are going to select is going to take 5 cycles. So the instruction latency is always going to be 5 cycle, and this was the same thing in the previous case as well. So if you go to the bank, you're still going to take the same amount of time. Your time is not changing. Your time is not changing. You're still going to take the same amount of time. What is changing is the throughput, or the number of tasks that are being completed to improve the performance. So in the same case in the bank, if there are 3 customers coming one after another, and you are having some overlap, what's happening is each customer is taking the same amount of time, but uh, the overall time, the overall processing has improved because you have more customers satisfied, right? So if you look at this diagram over here, and starting from the fifth cycle, you're going to see that a new instruction completes in one cycle. So what is the effective delay in this case? So you can see here that in other words, what you can say is that instruction 1 has taken 5 cycles, but instruction 2 has now taken just 1 cycle, instruction 3 has 1 cycle, instruction 4 has 1 cycle. So you're completing one instruction per cycle, okay, except the first one, which is taking more time, right? So latency has not changed, but the servicing has changed. So you are finishing one job per cycle, and this is the throughput. So if you're talking about 10 cycles, you're going to see that 6 instructions are completed, and your instructions per cycle are zero point 0.6. So you want to find out the speed up. So we have discussed the speed up in the very first class. So speed up in this case is again from the same formula, that if you're comparing it from a non-pipeline procedure, then one instruction was taking 5 cycles, right? So this means if you have got n instructions, they are going to take k is 5 over here, so they are going to take n into k into tau, which is tau is the cycle time, right? So the for a non-pipeline process, this is going to be time for n instructions. If you're talking about a pipeline process, it would be the first will take k time units, but the remaining will take just one time unit. So you can say k plus n minus 1. The first one is taking k time units, but the remaining n minus 1 are taking just one time unit, right? So you have got k plus n minus 1 tau, and this is going to be the speed up that is going to be achieved, right? Now for explaining the pipeline, you have to consider some architecture before that. So we are going to go with the MIPS pipeline, MIPS process, and this MIPS processor, and this MIPS stands for microprocessor without interlock pipeline stages. I'm going to come to that, what is pipeline interlock. And when this processor was designed, it was without any hardware unit to detect hazards and insert stalls for that. So that's a different thing. I'm going to come to that later. So this is the diagram showing you the MIPS internal architecture. I'm going to come one by one for every stage. Okay. So what we have done is divided that process into 5 stages. So our first stage is instruction fetch. So in instruction fetch, that's our first stage, and every instruction has to go through that. And this is going to remain same for all the instructions. So what happens in instruction fetch stage is that we fetch an instruction. So all the instructions are of 32 bits. So we are going to get a 32-bit number from a 32-bit value from memory, right? And why am I calling it a memory? Why am I calling it a value? Because the memory does not know what that particular instruction is. A memory will never knows what that instruction is, because that instruction is with respect to the processor. So the memory is going to be provided with some address, and is going to give you some 32-bit number, 32-bit value, or 32-bit word, right? So that's an instruction fetch step. So you're going to give a program counter. So program counter holds the next instruction's address. Your program counter is going to hold that address. That address is going to provide it to the memory, and then it's going to give you some 32-bit word, and that word would be stored in some register. Now, before going to further, I'm going to come back to with a convention over here. So we have defined five stages, and these registers are named according to the stage which is there, according to the stage that they are separating. For example, if this is the fetch stage and the next is the decode stage, then we are going to call that register as if/id, which is going to identify that this register is basically the one between the fetch stage and the decode stage. Okay. Now, what other task is required here? So we have the instruction available to us, and the second thing that we are going to do is we are going to add 4 to the program counter's value, the last value, and give that as the next program counter input to the program counter as well. So both of these things are going to happen in the fetch state. This PC plus 4 is actually pointing to the next address. So in a MIPS processor, all our instructions are of 32 bits. So that means that if you want to get to the next instruction, you just have to add a value of 4 to that address, because every memory address is of single byte. So if you add 4 to that, this means you are referring to 4 bytes difference, and 4 bytes difference is 32 bits. So you are basically pointing to the next address, next instruction, right? So we update the value of PC plus 4 like this. But that's not always the case. That is the case if your next instruction is the sequential instruction. But sometimes it happens because of branch instruction, your next instruction is not your sequential instruction, and it has to come from some other input, some other branch, relative branches. That address is a different thing. We call that as a branch target address, and that is calculated separately at a later stage. But there is a provision for that. So this multiplexer is provided for that reason, so that it can select the PC plus 4 or something value coming from the branch target address, right? So both of these steps happen in the fetch stage. Now, the second stage is the decode stage. Before going to decode stage, I'm going to briefly describe the different instruction formats that are available in MIPS. So in MIPS, an instruction can either be an I-type instruction, or an R-type instruction, or a J-type instruction. So when you talk about an I-type instruction, we say that instruction is I stands for immediate. An immediate type instruction has got 16 bits of immediate value, right? In all these formats, all these three formats, there are 6 bits for opcode, right? There are 6 bits from opcode, and these bits are your most significant bits, right? So they start from so this is your 0 to 15 is the immediate value, and then the next 5 bits are the register code, and the next 5 bits are the register code, and the next 6 bits are the opcode. So 5 bits of register code means you have 32 registers, right? So this is a very simple format. You have 2 register codes, an immediate value, and an opcode, right? So this is an I-type instruction. So when you come to an R-type instruction, in an R-type instruction, you have these the R stands for register type. In a register type instruction, you're always talking about some arithmetic operation between registers, right? And for that we have got a different field here, but you can see here that the values, three of these values like opcode, rs and rt are same. So there are other fields required for operations when you're talking about register operations like add. So if you are going to add two register and store the result in the third register, you need three register codes. So you need at least 15 bits for those. You don't need any immediate value. Then you can have some instructions which might need shifting of the register contents. So then there are 5 bits because the register is of 32 bit, and then if you want to shift that register, you can have a maximum 32 shifts available. So these 5 bits are the shift amount. How much shifting do you need? These 5 bits, it's not, the pointer is not working in the zoomed. Okay, so these 5 bits are the shift amount, which is telling you how many bits that you have to shift if it's a shift instruction. And then there are 6 more bits for the function. So when you're talking about an opcode of 6 bits, this means you have a possibility of having 2 raised to power 6 operations. So if this is 6, this means you have got 2 raised to power 6 operations, which are 64. So you can have 64 operations, which is a very small number. They are different adds, and then they are different multiply and subtract. So, and there are many arithmetic operations. So but an opcode of 6 bit is just going to differentiate whether you have an arithmetic operation or not. Then you can further differentiate them by another function field. So you can have 2 raised to power 64 again, 2 raised to power 6 or 64 operations more depend. So this is a two-level decoding. So the first 6 bits are going to be decoded in the decode stage, and then the next 6 bits are going to be decoded in the execution stage. And these 6 bits are going to go for the ALU to determine what different operations the ALU can perform, right? So the ALU has can perform 64 different operations. This function field can tell what particular operation is required, right? So this is a different format. And then we have the J format, which is for jump format. This is a special format which has just got 64 6 bits for opcode, and then we have got the remaining bits for the address, right? And then this address is 26, and you can add 2 more bits to it because it jumps always to a byte point at a difference of 4 bytes. So that's another thing. But the main thing here in all these instruction formats is all the first 6 bits are the opcode. So it makes easier for the decoder, because this, whenever you're in the previous stage, when you have fetched the 32 bits, then you are going to separate these 6 bits and go give those 6 bits to a decoder, and separate those 5 bits and these 5 bits and start reading the registers. Okay, right. So this is our second stage, which is instruction decode. Now, what happens in instruction decode is we decode the instruction. That's the first thing. And the second thing that we are going to do is so this is the decoder part where we are going to decode it. So the 6 bits are going to go over here, and then we are going to generate control signals. Then we have this register file over here. So the two register RS and RT values codes are given over here, and you read two registers. The other thing that's going to happen is you are going to, if it's an immediate field, or if it's not an immediate field, the first 16 bits 0 to 15 are taken, and you're going to sign extend them to 32 bits so that it's going to be used in the next stage, right? So these are the steps that are involved over here. So you're going to decode it, and then you are going to uh, generate those control signals, plus you are going to read the register. So I don't have much time, so I'm going to quickly go through these stages. So this is what happens in the decode stage mainly. So you're going to do three things. you are going to generate control signal, you're going to read the register, and then you're going to sign extend the values, sign extend the immediate values. Now, why I had discussed the instruction format before this was to tell you that immediate value was only for the I field, for the I type instructions, but not for the R type or J type instruction. But in the decode stage, what you're going to do is the 32 bits that you have obtained from the previous stage, and they are stored over here. You're going to split that into different parts, and whether it's R type, I type, or J type instruction, you're going to take the 16 bits and give that to the sign extender, and it's going to give you some 32 bits sign extended value of that number, whatever the number that becomes. And if you want to use it, you are going to use it in the next step. If you don't want to use it, you are not going to use it, right? So for R type and J type formats, you are not going to have any use of these, but you are still going to compute the sign extended values. Now we come to the third stage, which is the execution stage. This is the main stage where you are going to perform the execution, or the ALU is there, and then we have the 6 bits that were the function bits also coming in, which is going to tell the ALU what to do. And then the adder is going to add the contents of RS and RT, which are the two codes, the source register codes, or you can have an immediate field as well. So the operations that are possible are RS with RT, uh, or RS with an immediate value, right? So these are the possible operations here. So you cannot have an RT with an immediate value. You can have always RS with RT or RS with immediate value. So if there are two registers, that is RS and RT always, and if they are register and immediate value, that is always an RS register in this case. Okay. Then there is a separate adder over here. This adder is for the branch instruction, and it's going to calculate the branch target address, right? So this adder is there for the branch instructions, and it's getting the value of program counter from the earlier stage, and the immediate value, and it's going to add and give some new branch target address if required. Okay, so we have discussed that, and the branch target address as well. Now, the fourth stage is the memory stage. And the memory stage is only used by load instruction or store instruction. So the load and store are special instructions. So in a RISC processor, normally what happens is you don't allow memory operations to be done uh, by all the instructions. So you have special instructions that are going to get data or store data. So load is to get data, and store is to write data. So this stage is only used by these two instructions, and all the other instructions are not going to like add and subtract, or other arithmetic instructions are not going to use that particular stage. At this stage is there because whenever you're going to design a pipeline, you have to look for the instruction which is going to use all the steps, and that is the load instruction. So you design it considering load in your mind, and for other instructions you have to, if you're not going to use any stage, you still have to go through that stage. So that's the memory stage, fourth stage. And the fifth stage is the write back stage, which is shown as a multiplexer over here, but actually you are going to write the register contents. So the register file is not shown over here, but it's shown in the decode stage. So what we do is write the registers value in the last step. That's the last step where you're going to store the result. So these are the 5 stages in which we have broken that instruction down, instruction steps into. I'm going to finish over here because it's 9 o'clock. So this is just an introduction of MIPS, and in the next class I'm going to talk about the different problems that can come in pipelining, right? So I'm going to stop over here, and we are going to continue with how an instruction is going to execute, but I'm going to give you some simple slides for your understanding, and we are going to start from pipeline hazards in our next class. Okay, so our next class would be on Thursday, but that would be our 8th class next Thursday, inshallah. But that would be our 8th class, and we have described that anything that we are going to study till the 8th class is basically going to be included in our midterm. So let's see how much we can cover in our 8th class. That would be part of our midterm. I'm going to take midterm on Sunday because I usually take midterm on a free day, not on on a regular day, because it gets easy for students to prepare for it. So I'm going to take some Sunday after after 1 week from our last class that is included in the midterm. So our next class is let me just check. Our next class is going to be inshallah on 20th of August, which means our midterm. Okay, so there is a problem over here. That would be Ashura holiday. So then I'm going to take midterm on 6th of September. Okay, so we are going to have a next class on 20th, and then we are going to have our next class on 27th. Both of them are Thursday. But then we are going to have our next class on 3rd, and we are going to have another class on Sunday of that same week, and we are going to have two classes, and that is also going to compensate one of the classes that we missed, right? So we are going to continue on Thursdays, and in the first week of September, so I'm going to have midterm on 6th September for the courses that we have covered till the 20th August class, right? Okay, right. So I'm going to stop over here. So what will be the pattern of midterm? Right. This would be a different midterm than the regular midterm, right? Because we are going to have it online, right? So online means that I'm going to give a PDF file or maybe a Google form. But it's better if I give you a PDF file, but you have to do it by hand, right? So doing it by hand is much easier because some of you don't have PCs, or maybe there are some electrical problems, power outages. So it's better if you do it by hand. So I'm going to provide you with a PDF, and I'm going to give you 2 hours or 3 hours for that, considering time for uploading the paper as well. So you're going to have something like 30 minutes for uploading that results, because normally uploading might take more time or less time. So I'm going to adjust the timing according to that. So but that would be an online midterm. So nothing is physical in this semester till yet. Okay. So the pattern is going to be, so it would be an open book, because if it's online, then it would be open book. So you have to you don't really have to remember anything, but you never know what's going to happen in the final exam. Final exam is more expected to be on campus by that time, so that won't be open book, but midterm would be open book. So I'll try to give you some examples or design questions which are going to be open book. Okay, so we are going to continue, and we are going to do whatever we have studied till the 20th, till the 8th week class, and from then onwards that's included in the final exam. Okay, so if there are no questions, I'm going to stop over here, right?